This is a demonstration of how to implement the space filling curve tool within certain polygonal areas of interest. Here we have a shapefile of the Bahamas as an example, representing the land area of the Bahamas. There's a sub-area, which we've identified here, which contains the population where we want to put plots. Within this sub-area, we can look at the attribute table, and we see that there are certain polygons within here which are going to represent the population. These are labeled with forest. So the first thing I want to do is I want to subset this subset area such that only polygons of forest are going to be in a separate file. To do that, we'll just simply use the select by attributes command. We will say, from within the attribute table here, we will say the class double click equals, and we'll get the unique values, and we'll say forest. We can also see that there's a mangrove class, and in this exercise we're assuming that mangrove also represents the population of interest. So we need to add something here, which will be an or, and then we'll say class equals mangrove. So it's forest or mangrove will get selected. So now that we have this, we can close this, and with our selection here we can create our subset. And we'll save it to the same location with a different name. And here I've just simply labeled it as the same name, the Pinelands with forest mangrove polygons. So I don't know if this looks correct, but it looks like only this part of the original Pinelands coverage, which is lit up, are the ones that are forest and or mangrove. So for some reason, none of this area has forest and or mangrove. I don't know if that's correct, but we'll proceed. The next step is to convert this new file that we've created, which we'll just turn on here, into a raster with ones and zeros in it. So the way to do this is first open up this new attribute file, and we will make a new field. I already did it here, but we'll just redo it. Say add field. I called it ones. It's a short integer, and I hit OK. So here it is. Then I will right click the heading of this, and I'll say field calculator, and I will fill it with a column of ones. So now that we've added the new column, what we need to do is project this to a meters-based projection. Currently, the projection is in WGS 84 degrees. We need to change it to the UTM zone associated with the Bahamas. If we look back at our map of the Bahamas, we're interested in this area, and if we go to this website, we can see that it appears to be in mostly this little area here. I mean, it's hard to say, but it's mostly in zone 18, and we're north of the equator, so 18 north. So if we go back to ArcMap, and we open Arc Toolbox, and we minimize this, then we say Data Management Tools, Projections and Transformations, Project, and we want to project the Pinelands data set that we just created. This is its projection system. What is the output going to be? And we want to navigate to where we are storing everything else. And we'll just call it underscore UTM 18. Save. And our output coordinate system, we will say a projected coordinate system, UTM, I think we do North America here, and we will say NAD 83 and WGS 84. Under UTM here, it's not in North America, it is in Northern Hemisphere. And we will go down to WGS 84, 18 north. That's what we want. Okay. And then we will say OK. Now we're ready for the next step, which is to go back to our Toolbox, Conversion Tools, to Raster, Feature to Raster. And the input will be the thing we just made in UTM Zone 18. The value we choose will be the ones, the column of ones we created. Our output raster, we will put it here. Notice that I already made this as an example, but it's going to prompt me to overwrite it, I think. We want it to have a descriptive name, and you have to manually type in .img at the end so that it will save it like that. And then the cell size I'm going to put as 20 meters, and I'll talk more about that later, but we might have to iterate, but we'll start with 20 meters. So I will run that. So after that runs, we could see that we have filled in all the area. This represents the whole population tessellated into 20 meter by 20 meter squares. And we see that it corresponds with the area that we just created. So what we're going to want to do is, so if this is the number of pixels of 20 by 20 meter pixels, we need to calculate how many 400 square meter pixels we will end up, points we will end up having associated with these pixels. So what we need to do is look at in the attribute table, we can see that there are 4,499,308 20 by 20 meter cells in our population. Then from my past experience, that tells me that's a reasonable number we could actually bring into Excel or somewhere else and do some operations on. So now we'll go back into our Toolbox. We will go to Conversion Tools, then from raster to point, and we're going to turn those rasters into points. So the input raster is this. The value is the only value that we can choose, and then we'll save this in our same location with a helpful name. And what I would do is call it Pine Island Forest or Mangrove _points.shp. And we'll save it and we'll run this. So when this finishes running, it takes a long time, depending upon what kind of computer you have. You will see that there is a very, very dense grid of points sitting on top of the raster, 1 point on each pixel. And you'll also see, if we get rid of this, you can see that these points fall across the original polygon coverage. And you'll also see in this new area that just by the luck of the draw, sometimes you get points that are falling right on the edge and they're actually not in the area. You'll get these little tiny things, which just because of the algorithm, it will not put a point in there, even though it looks like it might be bigger than 400 square meters. However, this point does receive one, and it just has to do with where the pixels sit on top of the polygons. So you can kind of see this, like here, there was no pixel that got associated with that polygon. Anyway, this isn't a problem, it's just something to be aware of, and it's, these things are obviously allowed to fall very close to the edges, within 10 meters of the edges of these polygons. So it would be hard to argue that there's any kind of a bias around edges. Although, because here you could see they're right on the edge, whereas over here, just because of the way the grid's set. And if you assume that the random starting point of the grid of elements here, of these points, these potential plots, it was a random starting point, I don't think you have anything to worry about, and you could defend it. So the next step is to go back to Toolbox, and we want to add the Partitioning Tools toolbox. So what you do is you right-click up here in the Toolbox area, and you choose Add Toolbox. We navigate to the location where we have the partitioning tools stored, and we just add the toolbox. And it should look like this. You should have the partitioning tools toolbox and then the two directories at the same level. Or the two, yeah. And these, basically the toolbox is the thing that goes in here, and it points to the scripts and the other information in there. So we'll open that, and then the partitioning tools toolbox will show up in Toolbox. We'll open it up. And here you have a couple of choices. The first thing we'll just do is the spatial order command. You don't have to do it like this, but this is what I'm recommending for you guys. Spatial order, and you'll see that the only thing we have to choose here is this set of points, and we'll add a new column to this set of points called order value, and then we'll choose OK. And it will run for a while, and you'll see that you'll see messages here scrolling across here. What it's doing now is it's building the fractal. It's connecting each of these points in a repeating way so that it will fill the entire space, and it will assign an order basically to each of these points. So as it goes through the whole study area, it will fill in, and then when it gets to the edge of a polygon, it jumps to the next nearest polygon, builds this fractal zigzagging across all the points, jumps to the next one, etc. And that's what we're going to exploit to choose the samples with different intensities. And now you can kind of see it runs so slowly. One of the reasons I was talking about choosing initially this 20-meter cell size was, we're connecting 4 million points, and it really just depends on your computer and how much time you feel like waiting. If I had chosen 10-meter pixels, these points would have been even closer to the edge here, maybe only 5 meters away, on average, and maybe this would have received a point. But there's a balance between how long you are willing to wait and how close to all the edges you want things to potentially appear. And in a practical sense, being 10 meters from the edge, is close enough, given the fact that this edge is not going to be geographically exact either, and given the fact that you're going to be out there with a GPS trying to locate the plot. So for any conceivable practical purpose, you have an equal probability of selection of all the points within this area. That could change, of course, if you have some very fine, detailed GIS coverages, and thus you want to be aware of what's going on here. After the points are generated, you can, for no reason other than to visualize the fractal, call up the tool called Points to Line from our Toolbox. You then select the points as the input feature, choose an appropriate output feature, and then you choose the order value as the sort field. When you run this, it runs forever. I stopped it after a while, so I only have a partial coverage. But you can see what it does is it draws the fractal line that connects all the points. So you can see exactly how the space filling curve divides up space. You can also see how some interesting things happen when there's discontiguous sets of points that represent these isolated islands. The curve jumps across space and can jump back and forth. Some of these things are an artifact of just the unique shape of these areas. But on balance, it does create a spatially balanced, as is demonstrated in the paper we did.